by thanking the organizers for setting up this really nice conference and for inviting me to speak. The plan, of course, originally was to be there in person and even stay for an extended part of the program, but it ended up being too ambitious to fly my son over the ocean in his first year. So unfortunately, we'll have to settle with Zoom, and I appreciate the opportunity to talk over Zoom anyway. So today I'll be talking about something that I'm really excited about, and my talk is going to be based on a paper that came out at the end of last year with Luis Apodo, Susanne Bitania, Alejandra Castro, and Christoph Keller. And before I get started, I just wanted to make sort of two preliminary comments. So obviously I'm not there in person, so we won't be able to continue the discussion during the coffee breaks, but two of my collaborators are. You already heard from Alejandra on Tuesday. And let's see, how do I switch the slides? And I really wanted to highlight Susanne, who's an amazing student originally in Amsterdam, but she's now a KITP graduate fellow for the next couple of months, so she'll be there during the entire program. So I really, I mean, I'd be happy to answer any question over email, but I really encourage you instead to go and interact with Susanne and ask her all the hard questions that she'll be able to answer, and I wouldn't be anyway. And the second question is, the second point is about questions. So one of the things that I've really enjoyed in this conference, apart from waking up in the morning and having many interesting talks to listen to right away, is the fact that it's been very interactive and people have asked questions during the talk. And so if it's logistically possible, I would encourage you to do it anyway. So please don't hesitate to interrupt me. Very good. So one of the major goals of understanding quantum gravity is to answer the following question. Can we characterize what the space of consistent and UV complete theories of quantum gravity is? And one of the beautiful things of AdS CFT is for gravity with a negative cosmological constant or for asymptotically anti-de Sitter boundary conditions, AdS CFT has essentially solved this question, or formally solved this question. And this comes really from the strongest form of the AdS CFT correspondence that says that the space of theories of quantum gravity in D+1 dimensional anti-de Sitter space is equivalent with the space of conformal field theories in D dimensions. And what we mean by that is the following. So this provides a UV complete and non-perturbative definition of what quantum gravity in AdS is. And what we mean by that is the following, is that the observables of a CFT at the local level is a set of local correlation functions. And given these correlation functions, we can always interpret it as giving us the amplitude of some scattering process in AdS. And because the CFT is sort of UV complete by definition and non-perturbatively defined, this provides a non-perturbative definition of quantum gravity in anti-de Sitter space. Of course, I'm being a bit cavalier here. This is why I put the word solved in quotation marks. So the problem is solved, not actually solved. And it's not actually solved for the following two reasons, is that currently we do not have a complete classification of all CFTs. And of course, achieving this is the holy grail of the conformal bootstrap program, but we're not there yet. So that's the first point. And the second point is that if we just grab a generic conformal field theory and we study its correlation functions, they will look nothing like what we would expect from semi-classical general relativity. And so, of course, perhaps every CFT is dual to some theory of quantum gravity in a formal sense, but the theories of quantum gravity that we're most interested in are those who behave like semi-classical general relativity and that are weakly coupled at low energies. Okay? But nevertheless, this is still a very useful way to organize the search, and you can really view it as a two-step process. The first step is to try to understand what are the conditions, maybe first the necessary conditions, eventually some sufficient condition that guarantees that a CFT admits a dual emergent description in terms of semi-classical GR. Okay, and we have a name for these theories. We've already heard this name many times in this conference. We call these theories holographic CFTs. And then the second part of the process is that once we have these conditions, we can use them to construct or to find, ideally, all CFTs of this type. Okay? And I won't have much to say about this second step in the talk today, but what Alejandra talked about on Tuesday is very much in the spirit. Okay, so here's how you should think about it. There's the blue region here, which is the space of all CFTs. That's what we'll call the landscape. There's a yellow region. I hope you can see my cursor. There's a yellow region, which are gravitational effective field theories. Okay, And the part of the yellow region which is not in the blue region, so this part here, is the swamplands. Okay, the part of the yellow region which is in the blue region is within the landscape and is where holographic CFTs live. Okay, and then there's two important lines on this plot. One of them I like to call the swampscape boundary, or the swampscape line. Okay, it's the line that splits between the landscape and the swampland. And of course, figuring out if you're to the left or to the right of this line is very difficult. Okay, if you just try to address the problem from the bulk, you start from a gravitational EFT. It's very hard to know if you're actually in the landscape. Sometimes you can easily conclude that you're in the swamplands. So that can be done, and sometimes fairly convincingly, but it's very hard to know if you're to the left of this line. So the answer is usually, am I in the landscape? Well, it's either no or maybe, and we don't know for sure. The advantage of the approach of thinking about holographic CFTs is that sort of by definition, you're in a CFT, so you know that you're in the landscape, and the only thing you need to figure out is whether you're to the left or to the right of this holographic condition line. Okay, and understanding what conditions, what holographic conditions are is just shaping this line a little bit. And I would argue that that's much easier than figuring out if you're to the left or to the right of the swampland directly from the bulk. So that's the advantage of this program. What I'd like to do, I mean, we already heard about them, so I'll go over this fairly fast, but just give you a small review of what the holographic conditions are. The first condition is that we want gravity to be semi-classical. And in the CFT, this maps to the large N condition. We can say that the stress tensor two-point function is parameterized by some number, N, which we take to be parametrically larger than 1. And there's a condition that's usually associated to this called large N factorization, which can also be stated as the fact that the CFT admits a planar or a fifth limit, which says that the light operators of the theory split into different sectors. There's operators called single trace operators whose correlation functions factorize in the large N limit. That's the first condition. The second condition is that we want the bulk theory not just to be weakly coupled or semi-classical, we actually want it to be local. And in particular, we want, higher derivative terms in the effective action to be suppressed. This condition is known as the large gap condition, which was put forward by Hemsker, Konedonis, Polchinski, and Sully, which says that if you look at the spectrum of the theory and you look at the single trace operators, the scaling dimension of all single trace operators with spin greater than 2 is greater than some delta gap, which is parametrically larger than 1. Okay. And I've stressed here that this is about the spectrum of single trace operators. There's always going to be multi-trace operators that have spin greater than 2 in low scaling dimension. So it's really important that it's single trace operators here, and we'll come back to this in a little bit. And finally, there's a third condition that will not play a direct role in this talk today, but I still wanted to mention, and it comes from very different physics. It comes from demanding that the entropy of the CFT matches what you would expect from the Bekenstein-Hawking formula in the bulk. And this is known as the sparse spectrum condition, first studied by Hartman, Keller, and Stoika, and it puts a bound on the density of light operators. Okay. Now, originally, the large gap condition was really a conjecture put forward in the HPPS paper, and a lot of work has been done over the last couple of years to try to prove it. And eventually, this was accomplished. There was first a proof of the delta gap condition at delta gap equals infinity, namely that if you have no higher spin operators in the theory, then the higher derivative couplings must be set to 0. And more recently, there's been very exciting progress using dispersive sum rules that can do even better. It can now give tight bounds on the couplings of these higher derivative operators as a function of delta gap. So you can figure out the scaling with delta gap was already known, but you can even figure out the coefficients out front and give precise bounds. Okay, so we can ask our chairman if this makes him happy or not, but I think this is basically the potential end of an era. Okay, this is what the large gap condition was about, and this is essentially as close to a proof as what we're going to get.
Aren't you being a bit too optimistic, Alex? Because this is mostly about a few like 3-point couplings and things like that. I mean, you can ask the question about higher point couplings, and I think we know almost nothing about that, right?
Yeah. So the proof, well, I would say it's not just 3-point couplings. There's statements you can make about higher point couplings as well. some parts of the proof are most established for 3-point couplings. That's a very good first step. But I would say that, okay, it's maybe not a complete proof, but it's very close to being one, and that the technology that we have should enable us with some amount of work to get there.
I like your opinion. Very good.
So I guess our chairman is not that happy in the end. Very good. That being said, even with this recent progress, and even if we assume that we can do this for all higher point couplings as well, which hopefully eventually will be the case, it's still maybe not quite the full story. And I wanted to mention some remaining open problems. One that has been pretty extensively discussed in this conference, and it's very exciting to see that people are thinking about this, is the subject of internal manifolds and scale separation. So we've heard many interesting talks about this, and one question, of course, is the existence possible. There's another question related to this that I think has not really been touched on so much, is locality in the internal manifold. Is it enough to have a large delta gap? Does that imply that the theory is also local on the internal manifold? And I'll say something about this maybe at the very end. And finally, there's another, I think, open problem, which is confronting a little bit the ideas of HPPS and HKS. And one way to phrase the problem is, imagine you find a holographic CFT with a parametrically large gap, but it has many operators. So many scalar operators that the growth is, faster than exponential. It goes like e to the delta squared. Can a theory like this exist or not? If it can exist, it says that the large gap condition is not sufficient because you'll violate the HKS bound. If theories of this type are inconsistent, maybe the large gap condition is sufficient. But this remains an open problem that I just wanted to mention. Now, all of this is great, but the problem is that there's a misconception that I hear way too often, and it has to do with large N factorization. So I tried to not commit to whether the conditions I was showing were necessary or sufficient, or tried to say nothing. And in fact, large N factorization is not even a necessary. Okay, and this will be a central point in the talk today. And the reason for that is the following. If you have a CFT that has large N factorization, what it implies is that the bulk effective theory is of the following type. You'll have the Einstein-Hilbert action for the gravitational sector. And then your matter sector will look something like this, where all the couplings of the bulk matter fields will have explicit dependence on G Newton. Here I imagine that G3 twiddle is an order 1 number. Okay? What this means is that all cubic and higher couplings are really Planck expressed. Okay? And there's no need for this to be the case. This is not necessarily at all. And in fact, if you think about it, we don't even really want this. If we want to make a connection with the physics of our worlds, eventually we'll need to understand, how do we take a strongly coupled quantum field theory like QCD or the standard model and weakly but consistently couple it to gravity. Okay, so the gravitational coupling is weak, but the quantum field theory that we start with can be strongly coupled. So the question we would really like to ask is, which strongly coupled QFTs can we couple to gravity? Okay, and I think the misconception has sort of two origins. One is that it's historical. All the canonical examples of AdS CFT that are of this type. The other one is practical, is that if you do have large N factorization, well, you have a single sort of perturbative parameter that you can work with, which makes your life easy. Okay, but once again, I would like to stress in no way is this necessary. So what we would really like to understand is, okay, how do we consistently couple, strongly coupled QFTs and AdS to gravity? And like I just said, this cannot be done with large N factorization. Okay, so if you're looking for a bulk Lagrangian that looks like this, eventually maybe one day we'll put the standard model here instead of a simple scalar theory. But we need to break large N factorization. Of course, we have to be careful what we do because we still want gravitational interactions to be weak. So we want to have that the correlation functions of the stress tensor do factorize, but this does not need to be the case for the other light operators. Okay, and maybe I can make some preliminary comments, is that I think this is much less explored than the standard or canonical holographic CFTs that factorize, okay? Like I said before, all the canonical examples, n equals to 4, ABJM, the D15 CFT, the 2,0 theory, you name them, they all have the property that they factorize at large N. And theories of this type are much less studied. there's some things that you can do where you can add branes in the bulk, or you can try to have an RG flow that flows to something strongly coupled in the IR. But typically this will involve deforming the CFT either by adding interfaces or by deforming by relevant operators. So it's sort of outside of the standard setup. Okay, and there's some important questions that we need to understand to tackle this is, how do we ensure in such a context that correlation functions of the stress tensor factorize if the matter doesn't? Okay, and you might ask, is large N enough? If you have a large CT, a large stress tensor 2-point function, are you guaranteed that the stress tensor factorizes or not? And I think this is an open problem that hasn't been explored. And the other important point has to do with the large gap condition. If your matter is strongly coupled, you don't know what the large gap condition becomes, because the large gap condition was a condition on single trace operators. Once you break large N factorization, there is no distinction between single and multi-trace operators. They're all light. There's no way to tell them apart. And as I said before, there's always multi-trace operators of spin greater than 2. So you're going to have plenty of operators with spin greater than 2, and it's not clear what you need to impose. Okay, so it's not clear what's going to replace the large gap condition. So the goal for today is the following. What I want to do is I want to introduce a general mechanism to do this. A general mechanism to produce holographic CFTs where the matter sector is strongly coupled. And as we'll see, this can be achieved by turning on exactly marginal multitrace operators. In fact, it's even better than having just a holographic CFT that's dual to strongly coupled matters that you can even interpolate. Okay, you can start with the standard setup where all interactions happen at the Planck scale. You can first go to a regime where the bulk matter theory is a perturbative quantum field theory, but perturbative not in the Planck sense, it's perturbative at the AdS scale. And then eventually you can go to a genuinely strongly coupled. Okay, so that's the goal. So as I said, I want to achieve this by turning on an exactly marginal deformation. So this is how it works. This is a general CFT statement for now. You take your CFT and you deform it by turning on an operator whose scaling dimension is D, a scalar operator whose scaling dimension is D, and whose scaling dimension does not receive corrections under this deformation. Okay, often this is done thanks to supersymmetry, but you could imagine that it's done in other ways as well. Of course, we're doing this in a large N theory, so we want to keep track of a couple of things. And we imagine that we start from a standard setup where the theory does factorize, and we're going to deform a way to break it. That means that we need to keep track of certain N scalings. And so we should rewrite this in a slightly different way. So we're going to take our CFT action, and we're going to deform by an operator. And so here I've pulled out the explicit N dependence that we want to put. From now on, lambda will be thought as some order 1 number. And we also need to specify the type of operator that we deform by. Is it single trace or multi-trace? Okay, so the K here is going to label the number of traces of the operator. And as we're going to see on the next slide, different things happen depending on what you do with beta and K. Okay, so there's various effects to keep in mind. The first thing that we would like to make sure is that our theory continues to converge in the large N limit. Okay, and this imposes some conditions, because obviously if you take the power here and you make it very large, you go to higher and higher order in conformal perturbation theory, you get higher and higher powers of N, and everything will blow up in your face when you send it to infinity. Okay, so there are conditions, and the condition is pretty straightforward to see, is that for the theory to converge in the large N limit, beta needs to be smaller or equal to 0. Okay, it turns out that for I'm using a convention, by the way, where all 2-point functions are normalized to 1. You can see that, however, for single trace operators, you're allowed to put beta equals 1. You're allowed to put a positive power of N in your deformation. And that happens because when you do conformal perturbation theory, it's only connected correlation functions that matter, and those are suppressed by 1/n to start with. Okay, so for single trace operators, you can do a little bit more, but otherwise convergence in the large N limit tells you that beta should be non-positive. If you want to demand that your theory preserves large N factorization, so you keep a planar limit under the deformation, this is even more restrictive. This says that beta needs to be smaller than 2 minus K. And a comment, if you're trying to lift most operators of the theory, go to strong coupling, like we usually do, say in N equals to 4 super Yang-Mills. you have to do it with a single trace operator. They're the only types of operators that can take you from weakly coupled point to a strong point. Okay? But what you see is that there's an interesting window here where beta is smaller than 0, so you have convergence in the large n limit, yet bigger than 2 minus k, where you break large n factorization. Okay? And this interesting window here is what we're going to exploit. Oh, and maybe I should say related to this. So if you imagine that you start from a weakly coupled large n theory, and you want to go to a holographic CFT whose matter sector is strongly interacting, you sort of need to do it in 2 steps. You first go to strong coupling using a single trace operator like the gauge coupling. And then once you're there, if you have a multi-trace operator, you can turn it on in this particular way to now make the matter strong. So let's consider a particular example just to see how things work. And you'll see that it can be worked out in a lot of detail. So we can consider a triple trace deformation with beta equals to 0. Okay, that means that we're deforming our CFT by the following operator. Now we imagine we start with a theory that has large n factorization. So at lambda equals to 0, the OPE coefficient between 3 single trace operators O is normalized in this way. Okay, this is what large n factorization tells you, and this little number COO could be 0 or non-zero. That doesn't matter. Okay. And then we want to deform, and we want to compute the first derivative of this OPE coefficient as you turn on the coupling. So that will be done by studying the 3-point function in the presence of the deformation operator. But this you can exploit the fact that the undeformed theory has large n factorization and just compute this by doing Wick contraction. So this boils down to the integral of 3 powers of the 2-point function plus 1 over n corrections that I'm suppressing. Okay, and then this is very easy to evaluate it and see what happens. So for example, we considered a very particular example in our paper, but this could be done more generally if you specialize to 2 dimensions and you take a half BPS operator. So you imagine you have 2,2 supersymmetry to stay simple. You take a half BPS operator whose weight is 1/6. Then there's always going to be a triple trace operator, which is phi phi chi, where chi is some super descendant of phi, who's exactly marginal, and whose scaling dimension is protected by supersymmetry. Okay, and then you can see how the OPE coefficient of these 3 operators changes as you turn on the deformation. Okay, and you can compute this integral explicitly in conformal perturbation theory, and here's the answer. Okay, so you see that the important point is that you started from an OPE coefficient which was suppressed by n, and now it's order 1, meaning that everything will start to interact strongly. Okay, so this is a great story, but you might be wondering, okay, fine, this is great, but when do you actually have exactly marginal operators? Maybe these things never exist or almost never exist. Okay, and the point is that multi-trace operators are not unicorns. They exist, and there's plenty of them. Okay. The first one that I heard about was in this beautiful paper by Aharoni, Perkuz, and Silverstein, and actually inspired a lot of this work. Is that in the Klebanov-Witten theory, there's an exactly marginal double trace operator, and this is maybe not as widely known as it should. Many of the reviews don't mention this because they sort of focus on the single trace marginal operators, but there's an exactly marginal double trace operator here. Okay, and the Klebanov-Witten theory is a fairly known 4D SCFT. If you go to 2 dimensions, Alejandro talked about it on Tuesday, the symmetric orbifold of the minimal models and their deformations to go to a putative strongly coupled point have plenty of exactly marginal operators. As a matter of fact, you can find exactly marginal operators of arbitrarily traced. This is special to 2 dimensions, but it can be done. So there's plenty of these operators. And I think there's no reason to expect that there's not a gazillion more. I think we maybe haven't focused enough on looking for them, but I think there's going to be tons. So it would be really interesting to find some in 3D SCFTs and in 4D SCFTs. You might ask what happens in the CFTs dual to AdS5 cross YPQ. Maybe there the spectrum is interesting enough that you get triple trace deformations and so on. Okay, so these things exist. There's plenty of them, and we just need to go out and find them. So let me just summarize what I presented. So I presented a very general mechanism to get holographic CFTs which don't comply with large N factorization and whose bulk dual is, weakly coupled semi-classical general relativity, coupled to a strongly coupled quantum field theory. Again, this mechanism even enables you to continuously connect sort of the standard holographic CFTs that factorize with those that are strongly interacting, and there's intermediate regimes which are very interesting. You can imagine studying, lambda phi cube or lambda phi 4 theory in the bulk, but consistently coupled to gravity. Okay, and as I said, you start with a sort of standard holographic CFT, and you deform it by an exactly marginal multitrace operators. These operators exist. There's plenty of them that we already know of, and I'm sure there's many, many more. We just need to go looking for them. Okay, and you can check that it's not just because you can deform by them that you're guaranteed that something happens. You actually need to go and check, and we did an explicit check in conformal perturbation theory, and indeed, the OPE coefficients become order 1. Okay, and I just want to finish with some open questions because there's still a couple. The first one is the following. What we really wanted to set off to do is, find the bulk effective theory with the following type of Lagrangian: Einstein-Hilbert term, and an order 1 cubic coupling or quartic coupling. Okay, and you can ask, did we actually achieve this? And it turns out that there's a subtlety here, and I should thank Shoda for bringing this to our attention. Is that when you go from OPE coefficients to bulk cubic couplings, there's actually a constant that multiplies them that maybe you don't worry about most of the time, which is basically some gamma functions. But these gamma functions can blow up at particular tunings of the OPE coefficients. Okay, and they can blow up sort of in 2 different ways. One is if the 3 weights align in this particular way, and the other is that if the 3 weights sum up to D. Okay, and it turns out that for the operators that we turn on, we turn out to be precisely at the case where one of these gamma functions blows up. Okay, and so this is worrisome because you might say if you try to put on a cubic coupling for these operators in the bulk, you'll get infinity from the Venn diagram. So this must not be what you're doing. And in fact, that's probably true. There's a very similar issue that arises for extremal correlators where these gamma functions blow up. And the way to think about it is that instead of adding a cubic coupling in the bulk like this, you should really add a boundary term, which essentially plays the same role because it does the same thing at the level of the OPE coefficient, but it's a slightly different manifestation in the bulk. Okay, and this was studied in great detail for extremal correlators many years ago. So something similar happens here. One thing you might worry about is whether the deformation that we turned on made the bulk theory non-local. In particular, if you have this issue of multitrace, of boundary terms in mind, you might think that the boundary term is inducing some type of non-locality. Now, from the evidence that we have, it doesn't seem like anything is becoming non-local. If you tried to study the bulk theory, I don't think you would see any traces of non-locality. The bulk theory might look a bit weird in the flat space limit because of these IR divergences issues I was talking about in the previous slide, but I don't think it would be non-local in any way. That being said, there is a but, and the but was actually discussed in this original paper by Hernan Berkuz and Silverstein and by some later work. Is that if these multitrace operators come from KK towers, so if you imagine, for example, in the case of the Klebanov-Quinn theory, comes from KK modes on T11, then there could be non-local effects introduced by these multitrace deformations on the internal manifold and potentially on the AdS space as well. Okay, and so this is interesting for several reasons. Well, okay, it's one reason to worry that something could potentially go wrong, although we don't really see it in any obvious way. But it's also interesting in the light of the large gap conjecture, because if you take a holographic CFT, you deform it by a multitrace operator, this time preserving large N factorization, so you stay within the framework of HPPS, it's possible that you introduce some non-localities on the internal manifolds, and so maybe the large gap condition is not quite enough in that regard. Okay, and all of this would need to be studied better. And finally, there's a potential issue that I don't think is a problem, but that one should still mention, is that if for some reason the conformal manifold that we're studying with these multitrace deformations was such that the multitrace direction is compact, and if it happened that the compactification radius of the moduli space or the conformal manifold is down by some powers of 1 over n, well, then we could not make the coupling order 1, right? Because if we tried to make it order 1, the only thing that we would do is go around the circle many, many, many times, okay? Now, I think we have pretty solid arguments against this. It seems that if you do preserve large n factorization, basically the derivative of the OP coefficient is constant, so I think you can go arbitrarily far in that direction. So the typical thing that we would expect is that the radius of these directions is order 1, not order 1 over n. And so, okay, maybe there's some limit on how big you can make the coupling, but it doesn't make the mechanism fail. Okay, but there's an interesting general question is, what's expected of the structure of multi-trace directions on conformal manifolds? And with that, I think I'm out of time. I didn't see Joao throw anything, but let me stop here and thank you for your attention.
Thank you. Yeah, I think it was perfect timing. Question here.
Hi, Alex. I have a question and a comment. This relates to how you think about multitraces in AdS CFT. So as you know, deforming by multitrace deformation essentially amounts to changing boundary conditions for the bulk field. You don't introduce new bulk of fields in the theory. So if I want to add a trace O squared operator, then I would put in a boundary condition that relates the normalizable and the non-normalizable mode in a particular way. Is it clear to you that if you add order positive powers of n for such boundary terms, the variation, that there's a well-defined variational problem with these multitraces, but it's not clear to me that the on-shell action is finite and makes sense and is order n squared, and whether even for such boundary conditions you would end up with finite on-shell sensible large n actions and stability of areas. So this question would have to be addressed before we say that there's a sensible way to couple these multitraces in the theory.
Good. So I'll answer in several steps because there were several different things. So the thing that you said is probably best understood for double trace deformations, this changing of the boundary conditions, for example, between delta plus and delta minus. It turns out for double traces, you cannot do what I said. So for double traces, if you look where
no,
double
Alex,
traces,
that's different. Changing from delta plus to delta minus is just changing from Dirichlet to Neumann. You can, whereas if you want to add the double trace deformation, you certainly can do it. That's adding a phi squared type term in the boundary term, not in the counter term.
Right. But so the point I wanted to make is that if you want to break large n factorization with a double trace deformation, you would need to put positive powers of n in the deformation parameter itself, and then you're not guaranteed that things converge. And I think, in fact, they won't converge. But you see, with triple trace deformations, where's the slide that I was looking for? With triple trace deformations, you can set beta equals to 0. That already breaks large n factorization. And it should be clear from this deformation here that the deformation converges. Because you see, you can go to arbitrary order and perturbation theory, and you'll just get correlators of the undeformed theory, which converge at large n. And you don't introduce any scaling of n here. So I don't think you destabilize the theory. The theory makes sense. You can take the large n limit. Yet what you do is destroy large n factorization.
And in particular, the bulk action is no longer order n, right? It's smaller because it goes so that's part of the goal, I guess. No,
the bulk. Sorry, the bulk gravitational action is still of order n squared. So
the gravitational part, but that is.
But yeah, the matter part is no longer of order n. But that's what you want. That's what we wanted to accomplish.
Yeah. Go ahead, Douglas.
Oh, I can't. Sorry, I can't hear the question.
I think you have to press.
Can you hear it now? I guess so.
Yeah.
Isn't the triple trace term that you added explicitly a boundary interaction of the bulk fields? It's just like those operators at the boundary, those are bulk fields near the boundary, and adding that term, the Lagrangian, is adding a interaction of those fields at the boundary. There's not a bulk interaction.
Yes, I think I agree, but to me the distinction is not so clear. So if you think about it from the CFT perspective, you know, what measures how coupled the operators are is the OPE coefficient. How you get that, whether you get it from a local interaction in the bulk or whether you get it from a boundary term, is maybe not so important.
But
so
more information about it in this case, because we can look in the bulk and see what it is that you did. And from the perspective of the bulk, what you did is you added an interaction between some bulk fields when they're out at the boundary. They do not interact in the bulk.
Well, let me, I mean, I think that's a valid interpretation, but it's not clear to me that that's really an issue, because we could go back to the case of the extremal correlators where this also happens, right? And now you have some bulk theory with many fields and they're all coupled. And many of the bulk terms many of the bulk couplings are non-zero, but if you scan through scaling dimensions, all of a sudden you would get a divergence. And what happens is that indeed at these particular values of the weight, you don't write the bulk term in the action, but you write a boundary term instead. But I'm not sure that changes the dynamics drastically. That's what I'm saying. You know, at the end of the day, in holography, everything is a boundary term, right? So
no. Here, the thing is that we can translate what you added, the term that you added, we can translate that directly into the bulk effective field theory. And it is a boundary interaction in the bulk effective field theory. Because
yes, I agree with that. And in fact, you should not write the bulk interaction in the bulk EFT because you would get divergent Venn diagrams. So you should not do that. So if you want, it's strongly coupled through the boundary instead of being strongly coupled in the bulk, but it's not clear to me why that's an issue.
It just is not what you. My understanding is it's not what you set out to do. You wanted to have the fields interacting in the bulk. That seems like it requires a more non-trivial modification of the boundary theory than this.
I think it's a matter of perspective, because the problem is that if you start out with scalar fields, I mean, it's a little bit of a kinematic problem, I would say, because if you start out with scalar fields of a particular mass, you simply cannot make them interact in the bulk. You will always run into higher divergences. So in some sense, but in the CFT, you're completely blind to this issue because you can do whatever you want with the OPE coefficient. So I would say that in some sense, the boundary term comes in to save the day and allow you to make them interact anyway. This is how I think about it.
Alex, I'm going to pick up what Douglas just said. I think there's a crucial distinction between the extremal correlators and your example. And
okay,
in the following sense. So it's true what you said here, that there is a divergence, which is cured by a boundary term. But this boundary term is different qualitatively because it's a boundary term that's there for holographic renormalization. It's a counter term that allows you to pick out the finite correlation that there is in this OPE coefficient that you cannot see from computing just a Venn diagram naturally. That was the point of the paper that you mentioned. However, when you want to change the boundary condition and add the triple trace, you just change the boundary conditions. So you change the variational problem for the bulk scalar field. This is consistent with what Douglas said. You are literally adding a boundary interaction. You're not changing the bulk dynamics. These are two qualitatively different things. If you just look at the boundary action, I agree with you that it looks like a boundary term. But the boundary terms have two roles. They're either part of the variational principle or they're part of counter terms, and they're just distinct.
But here, I think what I would say is that, you know, in some sense here, that particular term that you're discussing is just a free parameter. It's not fixed. You turn it on or you don't turn it on. It's up to you.
Okay, Simon.
Yeah, just to make sure I also understand the related question. If you have say QCD in AdS4 At weak coupling, it's a
Yeah.
theory of currents in the CFT. Do you think you can get strongly coupled QCD in the bulk by adding some double trace interactions in these currents? Do you think that's possible?
I haven't thought about it. I certainly do not want to claim that all stringly interacting bulk theories are of this type. So I'm not saying this is the only way to go. I don't know if what you're saying is possible. I'm also not sure you would preserve. I think in that case you would not preserve conformal invariance exactly, right? There's no reason for that thing to be exactly marginal. But if you're willing to flow, then many things can happen. Here, I wanted to do a setup where I'm guaranteed that I have conformal symmetry throughout the deformation. I'm not sure you can do that in QCD.
Okay. Any other question? Go ahead.
Okay. Would it be fair to say that the update of HPPS that cover the cases of strongly coupled KFT to gravity is to say it's large N in the stress tensor correlators and it's large gap in the stress tensor OPE? In other words, stress tensor correlators factorize, and if I do TT-OPE, the single trace of spin 4 has to be heavy. If I found the CFT with these properties, it will cover both the usual.
No, but I think there's a problem with the starting point there, is that if you do not have large N factorization globally, then you cannot talk about single trace operators anymore. So you can talk about the operators that appear in the TT-OP that you can do, but there will be operators that appear in the TT-OP that have spin 4 and that are light. Maybe they appear with a small coefficient, but they're there.
Yeah, I think they will be at the one loop order. So if we're talking about planar, so this single trace applied for planar correlators, so then there will be no spin 4 because all this matter will enter one loop.
Yeah, I think one would need to prove that, but so I think that's probably the way to go about it. But one would need to prove that so that if you have no, I think it's a question of what you start with, right? But in principle, there is a coupling which is TT to some other operator, right? That's like a non-minimal coupling that we can suppress at large delta gap when we know everything factorizes. But here you need to show that that coupling is also small.
And somehow I would think that the recent technology should still apply. These couplings will be small just based on consistency. So
yeah, but you have you have an infinite number of them now, right? You have the whole matter sector.
okay.
I think I agree with you, but one needs to prove this.
Okay.
Hi, Alex. Would it be in the spirit of what you have in mind to have instead, I don't know, some copies of, or maybe even different CFTs which you make weakly coupled, which you couple weakly among each other? I mean, here you are saying, oh, I want to add a small coupling to this scalar, but it seems similar to taking a pre-existing CFT. You take several copies of it and then you couple it with a small. This can be done, by the way, in several examples. Instead of adding this controversial boundary operator that I'm also confused about. This would be a genuine bulk coupling. Like class S, I don't know, where you make the tubes among the trinions very weakly coupled, or the defects in unequal force pyramids that I briefly mentioned.
Yeah, so, well, okay. Defects, I think, is a different story that I would not want to get into. I was on purpose here saying, let's, not.
No, sorry, just to clarify, you connect, the defects connect several copies of a CFT, and then the whole thing is still a CFT. Like interfaces in an equal, you start from n equal 4 superior mills, you put it on several intervals, and then you have interfaces that connect them. But anyway, if this example is confusing and not explaining it well, maybe think about class S. That's maybe clearer.
Yeah, so the thing with tensor, well, if I understood correctly, what you were proposing, you wanted to tensor, I don't know, usual holographic CFT. You want to tensor it times something which would be strongly coupled, right?
No. So I take many copies of ordinary CFT, and then I connect them with relatively coupled matter.
With something that's weakly coupled?
Like exactly. So in this is what you do in class S, right? The tubes have a gauge coupling to them that you can make very weak. So the several copies will communicate only very weakly. The stress energy tensor of each copy will be almost conserved.
Yeah, but that seems very dangerous to me, because if you have many copies that are only weakly coupled, then you're going to have, you know, basically higher spin currents that come from the composites of the stress tensors in the different copies. So that theory does not seem like it's holographic to me at all.
You almost have them.
Yeah, but I think it almost is dangerous. What we want is not we don't want to have even approximately.
These are standard. I'm not making this up. These are actually discussed in the literature. But anyway, we can.
Okay. Okay. Yeah, I'd be happy to see the references to see how it connects.
Okay. So in the interest of time, let's thank Alex again.
Thanks.